Okay, welcome back. This is our third lesson on radical expressions, and in this lesson we're going to investigate radical expressions and the concept of absolute value. Now, before we get started into this lesson, we need to establish something very quickly. Okay, what is 2 times 2? Well, we get 4. What is negative 2 times negative 2? When we multiply two negatives, we get a positive 4. Now, we're going to call this x and this x, and we're going to call the 4 x squared. So x times x. Question, x squared is what type of number? When we multiply a number by itself, what do we get? We get a positive number. So x squared is what? X squared is positive. Now, here we have 2 times 2 times 2 times 2. 2 times 2 times 2 times 2 is positive 16. And negative 2 times negative 2 times negative 2 times negative 2 is also positive 16. Look, every two negatives multiply to give a positive number. Every two negatives multiply to give a positive number. 4 times 4 is positive 16. So here we're going to say x times x times x times x equals x to the 4th. So what do we notice about x to the 4th? X to the 4th is also positive. And I want you to notice as well, x to the 4th is positive regardless. Could x itself be positive? Yes. Could x itself be negative? Yes. So x to the 4th is positive regardless of whether x itself is positive or negative. Question, is x squared positive? Yes. Is x squared positive regardless of what x is? Yes. X itself could be positive or negative. So now we're going to say general. We're going to make a general rule here. If x is taken to an even power, what type of number do we get? We get a positive result. Now, over here we have 2 times 2 times 2 gives positive 8. And negative 2 times negative 2 is positive 4 times negative 2 is negative 8. We're going to call this x times x times x, and we're going to call this x to the 3rd. Question, can x to the 3rd be positive or negative? Yes. Okay, so we're going to say here we have 2 times 2 times 2 times 2 times 2 gives 32. Negative 2 times negative 2 is positive 4 times negative 2 is negative 8. Times negative 2 is positive 16, times negative 2 is negative 32. Let me break it down. 2 times negative 2 times negative 2 is a positive 4. Negative 2 times negative 2 is a positive 4. So we have a positive 4 times a positive 4 times an extra negative 2. So 4 times 4 is 16, times negative 2 is negative 32. We're going to call this x times x times x times x times x. We're going to call this x to the 5th. And my question is, can x to the 5th be positive or negative? Yes. So now we look back. We're going to use backwards reasoning here. If x to the 3rd is positive, what do we know about x? We know that x is what? We know that x is positive. Backwards reasoning. If x to the 3rd is negative, what do we know about x itself? We know that x itself is negative. So we can make a conclusion backwards here. If x cubed is positive, we know that x is positive. If x cubed is negative, we know that x itself is negative. However, over here, if we say x squared is positive, well, x squared is always positive. We cannot make a conclusion about x itself. X itself could be positive or negative. So this lesson requires you guys to do some thinking. Okay, so x to the 5th could be positive or negative. Can we reason backwards? If x to the 5th is positive, do we know what x is? Yes, we know that x is positive. If x to the 5th is negative, do we know something about x? Yes, we know that x is negative. So, when we multiply x to an odd power, okay, so if we have x to some odd power, the output could be positive or negative. However, we can reason backwards from our positive result. If we say that x to the odd power is positive, we can reason backwards and conclude that x is positive. If x to the odd power is negative, we can reason backwards and conclude that x itself is negative. So this is the foundation of understanding absolute value with respect to radical expressions. Now let's look at the basis for radicals themselves. So if I say 5 times 5, 5 times 5 is 25, negative 5 times negative 5 is also 25. If I ask you what the square root of 25 is, we established this in the last lesson, is the square root of 25 plus or minus 5? No. Remember that a group of mathematicians decided to say that we're going to ignore the negative output, and we're going to say that the square root of 25 is just positive 5. So we're going to ignore the negative case. And this creates only one output. Why did they do this? Because they wanted the square root to be a function. Remember, functions have applications, and functions only have one output. We do not want the square root of 25 to be positive 5 one day and square root of 25 to be negative 5 on a different day, because this is two different outputs. This is not useful. Functions are useful because functions only have one output. So in order to make the square root a function, we have to say that the square root only has one output. And we're going to choose the most logical output and say, let's call the square root of 25 just 5, not negative 5. Can you argue that the square root of 25 is plus or minus 5? Yes, and it's a logical argument. However, by definition, we're saying that the square root of 25 is not negative 5, it's just positive 5. This concludes here that the square root of 4 is not plus or minus 2. The square root of 4 is just positive 2. The square root of 9 is just positive 3. So we're ignoring the negative case. Now, this creates problems of absolute value, and you're going to see why in a minute. Now, we've got to establish a couple things. So we're going to write the square root of a positive number. The square root of a positive number is a positive number. Look, we have the square root of a positive 25 gives what? Positive 5. Can you argue that the square root of a positive number is an output that's either positive or negative? Yes, you can. You can argue all day that the square root of a positive number, you can argue that the square root of positive 25 is plus or minus 5. However, which case is ignored? We're ignoring the negative case and just saying that the square root of 25 is positive 5. So which case are we choosing to ignore? We're choosing to ignore the negative case. So we're saying that the square root of a positive number is always positive. And let's make this more general. The rules for square root also apply to 4th root, 6th root, 8th root, 10th root. So we're going to say that the rules for square root, because the index is even 2, that this also applies rules for 4th root, rules for 6th root, rules for 8th. So the rules for square root apply to rules for any even index. So we're going to generalize here. We're going to make a generalization. We're going to say that the square root of a positive radicand, or I should say, if the index is even, then the radicand must be positive and the output is positive. Why am I saying that the radicand must be positive? Just out in left field for a moment. Let me ask this question. So square root of negative 25. The square root of negative 25, so we're asking the question, what number multiplies by itself to give negative 25? Well, we established this over here. When you multiply a number by itself, what type of number do you get? You multiply a number by itself, you get a positive output. So what number multiplies by itself to give negative 25? There is no such number at this point in this class. So we're going to call this non-real. Later in this class, are we going to investigate this? Yes. We're going to call this actually something that exists only in our imagination. Later in this class, we're going to call this an imaginary number. And we're going to study this as something that exists only in our minds, okay, as something in our imagination. Okay, so we're going to say that the square root of a negative radicand is non-real. So go ahead and write non-real. And this establishes our foundation. Now we're going to split this into two groups. So here up top we call this real, or this makes sense. So what's up top? Square root of a positive number makes sense. We're going to call this real. Square root of a negative number does not make sense. We're going to call this non-real for now. Now, there's an assumption written in your book, and I've looked at many textbooks, and it does not explain the concept. Very few textbooks explain the concept of absolute value. And I wish I would have learned this before I got to college, because when I got to college, it was extremely confusing. When my professor walked in and wrote this on the board, the square root of x squared is the absolute value of x. Then he turns around and writes this: the square root of x multiplied by the square root of x is the square root of x squared. This looks exactly the same because we can multiply the radicands together, but this is just x. So what is the difference between these two? Why is this absolute value and why is this not absolute value? I'm going to explain why right now. So there's an assumption written in your book, And the assumption is this, and it's not stated, and I'm just going to write it. Okay, so the assumption that's not stated, I should say, the assumption is not in your book. Okay, so the assumption that is not written in your book, but should be written in your book is this. Everything in Chapter 7, dealing with radical expressions, makes sense. Everything in Chapter 7 makes sense, or we call this real. Everything in Chapter 7 is real or makes sense. So what case are we dealing with? Everything in Chapter 7 is what? Everything in Chapter 7 is real or makes sense, meaning that anytime we have an even index, we're assuming something. We're assuming that the radicand is positive. So this is something that's not stated, but let's write. Okay, so this means that the square root of x, since we have an even index of 2, we're assuming something about x. We're assuming that x is positive. Now, the square root of x squared, we're also assuming that x squared is positive. Why? Because everything in Chapter 7 is real or makes sense, meaning that every radicand underneath an even index has to be positive, not negative. So the square root of x is positive, the x is positive, the x squared is positive, the square root of x cubed is positive, the square root of x to the 4th power, we're assuming that anything underneath the radicand must be positive. Now, before we get to this, let's go ahead and make sense of the absolute value concept. So I think this clears it up a little bit. So if we write the square root of, say, 3 squared, and the square root of negative 3 squared, quantity squared. Okay, so we first know that, okay, the radicand must be positive, and our output must be positive. We're choosing to ignore the negative case for the output. So we look at this and ask, what is this? This is the square root of what? This is the square root of 9. And this also is the square root of 9. Reminding you, what is 3 squared? 3 squared means 3 times 3, which is 9. And this is also negative 3 quantity squared. Negative 3 quantity squared. Are we squaring the negative and the 3? Yes. This means what? Negative 3 times negative 3, which is what? Positive 9. So you're looking at the square root of 9 and the square root of 9. And we've established that the square root of 9 is just positive 3. So circle this and circle this. So we're going to write the correct answer. Write correct and write correct. Okay, so we understand that the correct answer to both problems is positive 3. However, if I write this, okay, so we're now going to use our laws of exponents. We understand that the correct answer is 3. The correct answer is 3 because the output must be positive by definition. So we're going to now use laws of exponents by dividing our exponents. We're going to get 3 to the 2 divided by 2, which gives 3 to the 1st power, and 3 to the 1st power is 3. Over here we get negative 3 to the 2 divided by 2, which is negative 3 to the 1st power, which is negative 3. Uh-oh. Uh-oh. Our answer must be what? Our answer must be positive. Now, since there can be a negative number, remember if x squared, if the exponent is even, if the exponent is even, we know that x squared itself, we know that something squared itself is positive, but we don't know anything about the base. The base itself could be positive or negative. Notice over here. Our base can be disguised. So the base can be positive or the base can be negative. So how do we guarantee that our output is positive 3? We need absolute value around this to guarantee that our output is positive 3. The absolute value of 3 guarantees that this is positive 3. The absolute value of negative 3 guarantees that the output is positive 3. And we are remaining true to our definition. Okay, so now write this underneath this, the square root of x squared. I think this becomes apparent. Notice, so I'm going to underline x. Okay, question. What's underneath the exponent? X itself. Can x itself be positive? Yes. Can x itself be negative? Yes. So in this case, we don't know anything about x. Okay, so x itself can be positive 3 or x can be negative 3. So when we get x to the 2 divided by 2, we end up with x to the 1st power. Do we know whether x, what we don't know, could x itself be positive? Yes. Could x itself be negative? Yes. We know nothing about x, so how do we guarantee that x is positive? Or how do we guarantee that our output is positive? We need absolute value. And yesterday I said, or in the previous lesson I said that even divided by even results in an odd So here we have an even 2 divided by an even 2, resulting in an odd number 1 gets absolute value. But this is not always true. Absolute value, okay, because I showed you an example a minute ago that the square root of x squared is x to the 2 divided by 2, which is x to the first, which is absolute value of x. But if I write the square root of x times the square root of x, we also get the square root of x squared, which is even divided by even, giving odd. But this is just x. So you can't simply use this rule and say that even divided by even gives odd gives absolute value. This is not always the case. So this rule falls short. It's nice to know, it's a trick, but it doesn't always work. You have to understand what's going on here. Now, so we look at this and we say we don't know what x is. We don't know what x is. So at the end, we have to guarantee that our final answer is what? We have to guarantee that our final answer is positive, so we put absolute value around our x. Now, okay, so let's go to this for a minute. See if this over here, what I've written at the beginning, helps this make sense. So we're going to write the square root of x, okay, and we're going to write the square root of x squared, and the square root of x to the third, and the square root of x to the fourth. Now, okay, so I said that the radicand must be what? The radicand must be positive. Okay, the radicand itself must be what? Positive. So let's go ahead and underneath our x put a p. The radicand must be positive. So we know that x is positive. Now, in this case, because we know that x is positive, we can write at the beginning of this problem, x is greater than or equal to 0. I must state this. Positive, when I say positive, I mean positive or 0. I forgot to state that the square root of 0 is 0. So we can assume that, can the radicand be 0? Yes. So this is just kind of something that I need to say. So the radicand must be positive, or the radicand could be 0 itself. So the square root of 0 is defined. So I'm just going to say x can be greater than or equal to 0. So we know something about x in this problem. Now, x squared, however, by nature, what do we know about x squared? By nature, we know that x squared is already positive, so there's no need to say, our radicand is positive. We already know this. Okay, you can go ahead and put a p under x squared. You already know that x squared is positive, so we have nothing known about x itself. Notice, by nature, x squared is positive. But do we know anything about x itself? Could x itself be positive? Yes. Could x itself be negative? Yes. So do we know anything about x itself? Can we say that x is greater than or equal to 0? No. Because x could be greater than or equal to 0, or x could be less than 0. If x is positive, is x squared positive? Yes. Right here. If x is negative, is x squared still positive? Yes. So we know nothing. We know nothing about x itself. Now here we have x to the third. We can reason backwards here. We know that our radicand must be what? Positive. Now look here. We can reason backwards. If x to the third is positive 8, we know that x itself must be what? We know that x itself must be positive. If x cubed is negative, if x to the third we said was negative, we could reason backwards and say that x is what? X is negative, because a negative number multiplied 3 times gives negative 8. So we know that our radicand is positive, and since we know that x to the third is positive, we can reason backwards and conclude that x itself is positive or 0. We always say positive or 0, or x is greater than or equal to 0. So do we know something about x itself? Yes. Do we know something about x itself? Yes. Do we know something about x itself? No, not down here. Whenever we have an even whenever we have an even exponent, we know nothing about x. Notice, if the exponent is 4, or the exponent is 2, or if the exponent is even, we already know that this is a positive number. We already know that x squared is positive. We already know that x to the fourth is positive. That's great. But we don't know anything about x itself, because x itself could be a positive or negative number and still be positive when we multiply it together. X itself can be positive or negative, but when we find x to the fourth, we have no way of knowing whether our x value is positive or negative. So we know nothing about x itself. We know nothing about x itself. If I write the square root of x to the fifth, or the square root of x to the sixth, on x to the 6th, since our exponent is even, we know nothing about x. However, on x to the 5th, since our exponent is odd, if our exponent is odd, we can reason backwards. Since our radicand must be positive, we can reason backwards and say that our individual x value must be what? Our individual x value must be positive. So we can conclude before we start the problem that x must be positive, and there it is. This is going to establish when we use absolute value, when we do not use absolute value. We use absolute value when we need to guarantee, absolute value is used to guarantee that the answer is positive. We need to guarantee that our answer is positive. If we already know the answer is positive, then we don't need to use the absolute value. Watch this. Okay, so we're going to write here the square root of x squared. Now, we already know that our radicand is positive because x squared by nature is what type of value? X squared by nature is positive. So we already know our radicand is positive. However, when we get x to the 2 divided by 2, we get x to the first power. Notice, because of the x squared, we already knew that our radicand was positive. Do we know anything about x itself? Could x itself be positive? Yes. Could x itself be negative? Yes. Since we know nothing about x itself, what do we have to do? We have to put absolute value around the x to guarantee that it's positive. If I write the square root of x to the 3rd. Now, we know, because everything in this chapter 7 makes sense, everything is real, we know that our radicand must be positive. We know that x to the 3rd must be positive. Now, if x to the 3rd is positive, can we make a conclusion about x itself? Yes. We can conclude that x itself is what? X itself is greater than or equal to 0, or x is positive. So when we take a group of two x's out, we end up with what? X root x. Now, the question is our radicand still positive? Yes, because we know that every x in this problem is positive. So we know that our radicand is positive, which is good. Remember, our radicand has to be positive. And question, do we know whether the x on the outside is positive? Yes, we already know that the x on the outside is positive because there was an original assumption on the problem. Every problem comes with a known, or I should say every problem that has an odd exponent comes with an assumption at the beginning that we already know that x is positive. Since we already know that x is positive, do we need absolute value around it to guarantee that it's positive? No, we do not. So no absolute value is needed in this case. Hence, I should say this. We go back to the rule. Even divided by even gives an odd. This is absolute value. Here we have an odd exponent divided by an even. We don't need absolute value. Again, this rule is nice, but it doesn't always work. It's a trick. Now, looking at the square root of x to the 4th. By nature, what do we know about x to the 4th? We already know that x to the 4th is positive. But can we conclude something about x itself? No, we cannot. X itself can be positive or x itself can be negative. So we know nothing about x itself, but watch what happens. Here we end up with x to the 4 divided by 2, which is what? X squared. Ah, that's nice. Okay, so we want our answers. We already know that our radicand is positive, and we want our output to also be positive. But look, this is nice. Do we know something about x squared already? Yes. Notice, where are we? X squared is what? X squared is already positive. We know this. So since we know that x squared is positive, do we have to guarantee that it's positive? No, because x squared is what type of entity? X squared is a positive entity. So no need for absolute value here. Let's do a couple more problems. Okay, so let's look at some more. Looking at the square root of x to the 5th. Okay, so do we know something about x here? Yes. X to the 5th. X to the 5th. Well, I'm sorry. First, we know that our radicand must be positive because everything in this class, or I should say, everything in chapter 7 makes sense or is real, meaning that the radicand is what? The radicand is positive. So we know that x to the 5th is positive. Since x to the 5th is a positive number, we can reason backwards and conclude, since x to the 5th is positive, we can conclude that x must be what? X must be positive. So we know something at the beginning of this problem. We know that x is positive or that x is greater than or equal to 0. Since we know this, watch what happens. When we take our pairs of x's out, we end up with what? We end up with 2 pairs come out. Remember, we go to the next number below 5. The next number below 5 that's divisible by 2 is 4. 4 divided by 2 gives a 2, so we get x squared on the outside. And what's left? What's left over? Well, we took a total of 4 x's out. There's 1 x left. Question. Did we know that our x is positive? Yes. So is our radicand still positive? Yes, it is, because x is what type of number? X is positive, so we're still good here. What about x squared? Do we need absolute value around the x squared? Absolutely not. First off, we know that x is positive. Secondly, we know that x squared is what type of entity? X squared is positive. Now, let's do another one. The square root of x to the 6th. Here we're going to have absolute value. Watch this. So x to the 6th, we know already if the index is even, if the exponent is even, we know that this is already positive. So we already know that our radicand is positive. But the problem is, if the exponent is even, can we conclude something about x itself? No, we cannot. We do not know whether x is what? We do not know whether x is positive or whether x is negative. We don't know. So watch what happens here. We get x to the what? 6 divided by 2, which is x to the 3rd. Now we look at x to the 3rd. Okay, our output must be positive, but we know nothing about x itself. Since we don't know anything about x itself, look over here. We don't know whether x itself is a positive number or a negative number. Now look over here. What does that mean? We don't know whether x cubed is going to be positive or whether x cubed is going to be negative. So what do we need around this? We need what? Absolute value. Hence, do you see even divided by even resulting in odd? Yes. So this needs absolute value. Now, let's go back to the original question that I posed at the beginning of class. Well, or close to the beginning of class. I showed you this example. I think it makes it clear now. The square root of x squared. All right. X squared is what type of entity? X squared is positive, but we don't know whether x itself is positive or negative. So we end up with x, but since we don't know whether x is positive or negative, what do we need around it? We need absolute value. Okay, so there was no assumption at the beginning of this problem. However, if I write the square root of x multiplied by the square root of x, hold on, what do we know about all radicands? All radicands must be what? All radicands must be positive. Now, since we just have a single x underneath the root, and we know that this radicand must be positive, do we know something about x itself? Yes, we know that x must be what? X must be greater than or equal to 0. So we end up with, watch this, we already know from the beginning of the problem that x must be positive. So when we end up with the square root of x squared, which results in x, since we already knew at the beginning of the problem that x must be positive, there's no need to guarantee that x is positive on the end. So there is no need for absolute value in this case. Let's look at some other examples. I think this makes it very interesting. Let's look at these examples. All right. So a couple of examples from yesterday. Page 434, we had this example. The 8th root of x to the 16th, y to the 8th. Okay, so again, the rules for positive radicand, positive output, ignoring the negative output, apply to any even index. So not just square root, this applies also to 8th root. Now, so the same rules for absolute value apply to 8th root as they do for square root. So square root, 4th root, 6th root, and 8th root, any even index, 4, 6, 8, or an index of 2, all follow the same rules. So we're looking at 8th root. In this case, we first established our radicand must be positive. However, anytime we have an even exponent, we already know that this type of entity is positive. So we already know that x to the 16th is positive. We already know that y to the 8th is positive. This is great. We already know that these are positive. But because the index is even, we know nothing about the individual x. We don't know whether the x itself is positive or negative. So do we know whether x is positive? No, we don't know this. Do we know whether y is positive or negative? No, we don't. So we know nothing about x. We know nothing about y. We end up with this. Watch. 16 divided by 8, x to the 16 divided by 8, y to the what? 8 divided by 8. Here we have 16 divided by 8 gives what? X squared. 8 divided by 8 gives y to the first. But we look at our final answer. our final answer must also be a positive result. So, question, look at x squared. Is x squared already a positive entity? Yes. We're good here. This is already positive. However, y to the first power, do we know whether y to the first power is positive or negative? No. Whenever we have an odd exponent, we cannot tell whether the value of x is positive or negative. So what do we need around the y? We need absolute value around the y. Now we looked at this example. The fourth root of 3 x to the third y squared multiplied by the fourth root of 27 x y squared. Now, before we start the problem, I always establish what do we know. Okay, we know that 3 is positive. We know that 27 is positive. Remember, since the index is even, the whole radicand must be what? The whole radicand must be positive. Now, do we know that 3 is positive? Yes, we do. Do we know that y squared is positive? Yes, we do. Now we have to, this is a little trickier, so now we have to conclude something about x cubed. What do we know about x cubed? X cubed must be positive. Why? Because in order to have a positive value, we have to have 3 positives multiplied together. For instance, if x cubed were negative, think, if we had a positive 2 multiplied by, say, a negative 3 multiplied by, say, a positive 5, just for instance, positive times positive would give positive times a negative would give negative 30. So in this case, this would give an answer of negative 30. So remember, if 2 of them are positive, this must mean that the third one has to also be positive. Now, we already know y squared is positive. If something squared is positive, that's obvious. Anything squared is positive. Do we know something about the individual x? If x squared is positive, do we know anything about x itself? No. X itself could be positive or negative. So y squared is positive. Do we know anything about y? No, we don't. But x cubed is positive. Hold on. X cubed is positive. Can we conclude something about x? Yes. We can conclude that x is what? We can conclude that x is positive. So at the beginning of the problem, we have an assumption that x is what? Greater than or equal to 0. Same thing here. 27 is positive. Y squared we already know is positive. And since we have a positive and the whole radicand must be positive, can we conclude something about x? Yes, x itself must be positive. So we know here that x must be greater than or equal to 0. So at the beginning of the problem, we have an assumption. Our assumption is that x itself must be positive, but we know nothing about y. So watch what happens. Can we multiply the radicands together? Yes. 3 times 27 gives the fourth root of what? 81. X cubed times x gives x to the fourth. Y squared times y squared gives y to the fourth. And now we take out groups of 4. We're going to take 81, break it down. 81 is 9 times 9. Break this down. This is what? 3 times 3, 3 times 3. So we have 1, 2, 3, 4 3s making 81. We're going to take the 81, erase it, replace it with 3 to the fourth. We take out groups of 4. We take out a group of 4 3s. We get what? We get a 3. We take out a group of 4 x's. We get what? We get an x. We take out a group of 4 y's. We get what? We get a y. Now, the answer, because the index is even, the answer must also be what? The answer must also be positive. So we look at 3xy. 3xy must be positive. Is the 3 positive? Yes. Is the x positive? Yes. Look at the original. We already knew that x was positive before we started the problem. So there's no need to guarantee that x is positive because we already established that at the beginning. However, do we know anything about y? No, we do not. Since y has an odd result at the end and we know nothing about it, we need absolute value to guarantee that y is positive. Now, this is one of my favorite examples in this class. Okay, so let's look at this. This one will get you. All right, so we're looking at x to the 2/4 power. X to the 2/4 power. Ooh, all right, so we're going to have what? The fourth root of x. Let's do it like this. Let's go backwards. Let's write here. Let's write the fourth root of x squared, and we will conclude the video with this. So you have to be careful with absolute value. Absolute value doesn't just exist outside the root. Absolute value can also exist underneath the root. Maybe I'll show you a couple little examples here. So what do we have here? Well, the index is even, so we're worried about absolute value. Now remember, the radicand must be what? Radicand must be positive. Question, is the radicand positive already? Yes, it is, because x squared is what type of entity? X squared is already positive, so we're good. We know our radicand is positive, but the problem is, since we have x squared, do we know whether x itself is positive or negative? No, we do not. So when we reduce this, we get what? X to the 2/4 power. We write this in exponential form. 2 divided by 4. We get x to the what? 1/2 power. Now we rewrite this as the square root of x. And if you leave it like this is completely wrong. Watch this. Look at your final answer. Here we have the square root of x itself. Now remember, the radicand must be what? The radicand must be positive. But at the beginning of the problem, we knew nothing about x. We did not know. We did not know whether x was positive. We did not know whether x is negative. Because notice, x squared is already a positive entity. X squared, x itself can be positive, x itself can be negative. So since we don't know whether x can be positive or negative, and there's an assumption in this class in Chapter 7 that everything makes sense, that every radicand must be positive, we have to guarantee that our radicand is positive. What do we need around the x? We need absolute value around the x. So in this case, this is final answer of the square root. So what is the fourth root of x squared? The fourth root of x squared is the square root of the absolute value of x. And I think with this we can conclude the video. However, I do want you guys to write this in your notes. This will be on the test. This is by definition. What is the square root of x squared? The square root of x squared is the absolute value of x. If anything, I need you guys to take this out of the class. The square root of x squared is the absolute value of x. However, the square root of x multiplied by the square root of x is just x. Okay, so we do not end up with the absolute value of x. We just end up with x, and that concludes this video. Good luck on your homework, guys.